Hello, welcome. Please shut down your mobiles at first. Would be very nice. And the decks. Okay. FX will now tell you something about Cisco router security, and I wish you a lot of fun.
Ist schon an, cool. So, kann jemand die Musik ausmachen? Das ist irritierend. Anyway, Cisco iOS Talk, the annual, how should I say that, Felix Fetish report on iOS. I seem to be pretty much the only one finding this interesting. Anyway, what we have today, can we really turn off the music behind me? Thank you. Feels like being in an elevator or something. Second level, ladies' cloth. Okay, so we're talking about motivations of people that hack iOS, because like you probably don't believe me, but I tell you there are more people that hack iOS than just me. We're talking about the types of attacks, a little bit iOS architecture, detection challenges, methods, how to overcome those challenges, and a little bit on shellcode. So you see there's lots on the agenda. So bear with me if it is a little bit quick. We also have, because it is a attack and defense talk, a black hat-o-meter. So if you're a CISSP like I am, then tell your neighbor to wake you up for every slide that is in the upper area, and then everyone else can watch the slides on the lower area. So why is this talk a Cisco-centric talk? Well, the networks still consist mostly of those boxes. There's lots of money bound on the pure metal, so you don't just change your network gear every 2 or 3 years. So if people actually have a Cisco network, then they're going to stay with Cisco for a very long time. And this talk is also access layer equipment-centric, which is Cisco speak for cheap. So we're talking about those small boxes here, and not the big boxes, simply because we don't actually have big boxes. Or actually now we do, but we only have them for a week or so. In terms of other equipment, Juniper being the second biggest player in this market, from a attack and forensics point of view, they're actually just boring, because they're a not so free anymore FreeBSD. And so all the things that we know about FreeBSD, both from the attack and the defense, apply. The same holds true for your MediaMark plastic router, just that it has a Linux instead of a BSD. So this is why I find Cisco interesting. Really quick 2-minute, because people still ask me, why would you actually hack routers? And I'm like, because I love it. And then they ask, why would anyone else do it? So the thing is with today's host security, if you take this machine, you don't actually gain much, except for maybe if here's a firewall or something. But you actually don't gain much in terms of how you can attack the network from this point. And you can't do anything else to the other machines. If you take the switch, then all the stuff that used to work on hub networks actually works again. So you can break the separation, you can modify any traffic. And it's actually really hard for the end user to find out if the network is compromised or not. In fact, it's almost impossible. So there is no reverse NUC. There is no way for me to connect to a network and know that the infrastructure is not taken over already. And of course, if you take the router, then you also beat the network to the big bad internet, which can be useful. So on a bigger scale, this is how internetworks look like. So you have multiple routing domains. And they do have a bunch of security. They have like firewalls, IDS, IPS, or whatever your silver bullet of the day is, at the borders. Then they have ingress and egress filtering, which is just routing speed for there's stuff filtered, and they should have anti-spoofing, but it's still not globally deployed on the internet scale, which is sad. And then we have full trust in the core, because that's how the thing designed is. So you actually have to talk to each other and trust each other on the routing information to actually get data from A to B. So you can't really prevent anyone else fucking with you. So network security, therefore, is a hierarchical thing. So the higher up you in the hierarchy attack, the more you control, and the harder it is to find you. Like downstream defending is really common. Like if the ISPs wouldn't defend against people like you on the DSL lines, they would be out of business. But they can hardly defend against like the tier 1 they're linking up to. Because if the tier 1 tells them the internet is gone, that's exactly his point. Like, it is gone. So, so in this example, if we have our lovely international symbol for an asshole, and he takes this one router in the enhanced IGRP domain, he just controls the local network. If he's taking the border router, he controls all the networks, because if he controls the core, he can tell anyone where everyone else is, which I think is control. So some people still come up to me and say, well, yeah, that's no longer valid because we have HTTPS and SSL and SSH and all that, and everything is encrypted. Well, that is true. However, encryption and especially integrity checking only allows you to detect if someone else fucked with your message. Now, if you detect that, what are you going to do? That's really bad, because if it's in a corporate network, for example, you have absolutely no way to get around this. Because if the user could change the path through the network, like in this example, he will want to not jump over the red Cisco, that would be called source routing. And there is a very good reason this is turned off in the internet altogether, because then you can actually do a lot more harm than good. What is Mr. Kaminsky doing down there? So, all this is pretty much by design. This is how IP networks are designed. So, what's the attacker motivation besides the cool points I just made? Well, Windows and Unix become really harder targets, and iOS actually doesn't. So, because it stays around for a very long time and is not updated. And if it's updated, then it's updated with a new version that comes with new features. For example, a regular enterprise image comes with, in default, comes with a full voice XML IVM that is driven by Tickle scripts, which I've never seen anyone use, but it's in there and it's code that you can execute and that someone else could have fucked up. And backdoored iOS images become popular simply because people realized that it's a really, really cheap way of getting access to routers is to publish backdoored iOS images and then wait for all the people that try to get a Cisco certification to download them and run them in Dynamips. And when they're done, they try to port this configuration at work, and then they realize that only works with the same image. And then they copy the image that they use in Dynamips over to a real router, and out of the sudden you get access to something. So we actually need ways to handle those intrusions. Now, the type of attacker we're looking at here is not actually your arbitrary script kiddie. Development of reliable iOS exploits is quite costly if you have people that know how to do it. And yeah, they wouldn't just waste a zero-day exploit on an infrastructure if they're not really, really sure that it's going to work. And the idea behind this is actually to gain a foothold in an infrastructure and not to take over the router, do some shit with it, and then be done with it. So they want to stay undetected, and that prevented in the past people from actually developing too many of those exploits because it was a lot cheaper to actually take over the Windows or the Unix machines. Now, the modern rootkits that are used in banking Trojans, for example, are fairly expensive in development because they need to be fairly good. So it actually becomes cost efficient for a number of 3-letter or Unicode character organizations to develop Cisco exploits because they're now actually cheaper than a short-living Windows exploit. So types of attacks that we have, protocol-based, that's the well-known stuff. You participate in the network, you talk to protocol that the routers talk, and if they're stupid, they listen, and then you root. That includes things like DNS attacks or exterior routing attacks like shown from Alexander at DEF CON, where they took over like large parts of the DEF CON network. So this is the well-known stuff. The well-exploited stuff is actually functionality attacks. People use still weak passwords on Cisco's. My theory is you study about 2 years for the lab session of your CCIE certification. And in those 2 years, you have billions of configurations to cover. However, every time you set up a router, you type the password Cisco. And if you're conditioned 2 years to type the same password ever and ever and ever again, it's highly unlikely that you're going to change that in the future. So this is actually a big problem. Then the same holds true for SNMP communities, of course. And people still post entire configurations on the internet and say, look, this doesn't work. And then, well, you go and you decode the password because that is trivial. And then you go, okay, I know why it doesn't work and I can fix it for you right away. So that actually still happens. And then there's vulnerabilities, and 2 of them are really, really big. The HTTP level vulnerability is fairly old, and but if you look at proxy servers or other logging gateways on the internet, people are still scanning for this. Now, an arbitrary rule about black hats is they're not scanning for stuff that they're not expecting to find. So, by the fact that you're seeing a lot of people scanning for this, you can at least estimate that they find a lot of machines where they can actually get level 16 access by HTTP. However, it's very, very rare that people actually turn on the web server on their routers if they have a little bit of clue about this. So the other one is a really, really big vulnerability from 2008. So SNMP is used for managing networks. So you have to have SNMP in all the networks. Now, SNMP was always lame with the communities because it's a simple password string that sends a clear text over the network, and sooner or later people discovered that is a bad idea. Now, when they developed SNMP version 3, the main emphasis was on having a secure, cryptographically sound authentication. But there were also what I call byte cuspers. They try to save like 2 bytes in the network protocol message, and then they need like 500 kilobytes of codes to parse it. And this is pretty much what happened here. So they said, well, we are sending a hash or an HMAC actually over our community string. Now, the thing is this: if you take like half of an HMAC, cryptographically it should be pretty much the same statement. If you don't know why, then ask Rüdiger Weisfort. However, this is how they specified it. So they said, well, you can say a portion of the HMAC, and then this portion must match your calculated HMAC. Yeah, and the portion has a length field, and most people implemented it by the net SNMP code, which many people copied, and they implemented it like this. So they take the length field from the packet and the HMAC from the packet and compare it to theirs. Now, if someone says my HMAC is 1 byte, he needs approximately 256 packets to get access to the router. Full access, mind you. Now, the most amusing thing about this is it's a new vulnerability. Like all the router vendors had this issue because they all made the same mistake, sure. And so this is very widespread, and SNMP v3 is standardized as the control protocol for lawful intercept. Now, this is what we call Schäuble routing. This is where you can this is where you can tell a switch or router to actually mirror a port or give you parts of the traffic that someone else is sending from A to B. And well, those control messages are used to send them to the router and tell it, like, do this or don't do it. And they're designed so the system administrator cannot see this activity. This is really bad. Because all the routers in the internet need to talk SNMP, and it's really hard to maintain an access list on all interfaces for this. So this is right now the biggest threat to Cisco security, because of course they have this code issue. And you can essentially become your own Bedarfsträger for certain network traffic engineering that you have in mind. And then there is binary exploitation. Binary exploitation on Cisco hasn't seen so many published exploits. You can classify them essentially into pieces. One are service vulnerabilities, like services that the router offers. They're obvious places to look for vulnerabilities, but they're also unlikely to be in production networks. Like nobody with a sane mind runs an FTP server on a Cisco, except for having a very fancy place to store their porn. And then there is router protocol vulnerabilities. Those are interesting because the router needs to talk them. So an OSPF exploit is a lot more interesting than an HTTP overflow. Now, what do we have on the detection side? First of all, we have the very same mechanism that I just mentioned to be really broken, SNMP. This is what all people use for management. So it's a polling mechanism, but it's based on the MIPS, which is a database. And those MIPS are designed for network monitoring. So you can see how many packets go in and out and how the routes look and stuff like that. You can't see how many processes have I running. Did I get a new one? Did I get one that opens support? Stuff like that you can't see over SNMP. Syslog, on the other hand, is free-form messages, so you can actually get debug information out, but it's too slow and rarely used. So one of the actually quite useful detection and monitoring sites is config polling. There's tools like Rancid that actually go ahead and take all your configurations from the routers and diff them and analyze them and tell them when you got a new user, because that's usually of interest. For routing protocol attacks, the people are pretty much well placed. They have route monitoring. They see when the routing changes dramatically, so that is actually not a problem. Surprisingly enough, traffic accounting is actually a very useful source in network forensics, because people that route traffic, like ISPs, actually happen to have traffic accounting really well figured out, because that's what they get paid for. So they actually have detailed data on this. And it is quite useful to know who talked to whom at what point in time when you have an intrusion case and you try to figure out where they came from. So when we look at the types of attacks and then what we have in terms of defense, we look pretty naked on the binary exploitation side. And so since I constantly fail to come up with like weaponized Cisco exploits, I figured, nah. Well, the other approach is do the honeynet way and like build something to catch everyone else doing it. So we started looking into this. Because the common solution is try to lock everything centrally, with, even in a worst case, with debug messages, which are really slow and which actually stop the router while they're printed. So this is not good for performance. And then, of course, you need someone to actually parse those logs manually, because every single iOS version changes the output format, so you can't actually use a decent Perl script. Or SNMP, as I just already said, they just don't have the information you're looking for. Also, trying to detect exploitation while it happens, like in the moment the exploitation happens, has proven to really, really suck as an approach. It has been tried many, many times. Many of you probably have something, some fancy piece of software installed on their laptop that kind of like says IPS or something. But it's really, really hard. What you actually detect is what people did after they got a stable code execution. So there is another source of information that we can look at, which is the crash info file. Some iOS versions, later iOS versions, write a text file called crash info that contains memory dumps and register dumps and all that. It is meant for iOS coders, obviously, to figure out what they fucked up. The problem here is that in about 80% of all the cases, it is entirely misleading. Now, here's the thing. If you ever did any binary exploitation, you probably notice if your traceback says 424242440, then something very desirable happened. The problem is with this. If an iOS crashes due to, for example, a Stack Overflow, as it is here, it has a race condition, because the crash writer process tries to figure out what process actually crashed. And the analysis seems to be written so badly that he always ends up with himself. Which is why you see crash writer down here. What I found most amusing is in the latest iOS versions that I've seen, you can configure an arbitrary delay by hand. So they probably figured, we have a race condition, we have to wait some time. We have no idea how long, so leave it to the administrator. So what will those binary exploits actually do? They will actually patch the system in pretty much most cases. They want the router to no longer validate the passwords. They want the router to no longer lock. And they probably don't want the router to use any firewall functionality whatsoever. It is likely that this patching is actually going to be in the data structures and not in the code. The code is the more reliable place to do it, but the data structures are a lot harder to detect. Like, you can patch out the code that verifies your password, or you can set the VTY to authenticate it already. The latter is harder to do, but harder to detect. And they will probably also terminate processes. But we're coming back to this. So for detecting this, we actually need, what every forensics session actually needs, is we need a way to acquire our evidence first, and then recover information from that raw data, and then, make a more or less educated decision on what we see. Looking inside iOS, it's essentially the biggest ls program you've ever seen. It's one large ELF binary, and statically linked. It's loaded by a kind of BIOS called the ROM-on, and it runs directly on the CPU. There is no fanciness involved. There is a little bit virtual memory mapping, just as much as they need. They are not using any privilege levels of the CPU. Processes are actually not really processes. They're threads. They have a CPU context, and that's about it. So every process can write in everyone else's memory space because they all share one, which makes it interesting. They have a fucked up multitasking, but we don't care about this too much. What we care about is they have system-wide data structures, because they're one piece of software. They have one common heap. And they have very little abstraction around the data structures, which is actually the reason why it's so easy to fuck it up, because you're writing C. And if you're addressing the wrong pointer, and the pointer was actually a string or something else, it's really easy to have a string that turns out to also be a mapped memory area, and then you're writing somewhere in the memory without noticing. iOS boots actually from the ROM-on. It will load the image from Flash or network. Nobody does that. It may be self-decompressing, and it may actually carry additional firmware with it. So this is important for the analysis, that you're not surprised to actually see code that is not for the CPU platform your Cisco is for. The configuration is also loaded in text, and it's parsed on load. So you can actually have a wrong configuration. You could actually have a poem instead of a configuration stored on iOS. It will just line by line tell you that it doesn't understand it while booting. And if your poem would include the word shutdown, it would probably shut down an interface. The defaults that it applies if it doesn't load any specific information from you differ in every image, and there's no way to get them out. So the same configuration on a different machine does something entirely different. Everything is kept in RAM, which is a problem for evidence acquisition, because on regular common operating systems, the stuff you want to see, the stuff you're after in forensics first is non-volatile. So you take the hard disk. For iOS, that makes no sense, because all the information you want to see is volatile. So we need memory imaging, and we need memory imaging on demand, or if the device actually restarts, because that's the default behavior. If you are one big program and something goes boom, you pretty much have no option, because you have no idea what data structures are corrupted in what way. So you have to reboot the box, which is the default behavior, which sucks for evidence acquisition, because all the evidence just went out the window. So luckily, we also have some non-volatile evidence, but that's not really useful, because nobody would write into the NVRAM or change the configuration if they have a binary 0 day. Luckily, iOS coders have the same issue. So the boxes can actually write cores. They write a flat memory dump core, actually multiple cores, one for the main memory and then for all fancy memory that they have an individual one. And it's a perfect evidence, because it's a raw memory dump. There is no interpretation whatsoever. So the only thing we need is we configure the box to do it, because by default they don't do it. And I talked to many service provider people and large network people, and they all told me none of our boxes write core. For two simple reasons. The default behavior on failure is reboot, so they're not rare. So the boxes are optimized so they boot as fast as they can. So if they write core before they boot, it takes longer, and someone is going to notice the network outage, which is what they have redundancy for, but anyway. And also, well, it wasn't really useful for anyone except for iOS developers with an analysis tool that they supposedly have, and for exploit writers, because you could see where your stuff ended up. So we wrote a core dump analyzer, which takes raw core dumps and iOS images that were supposed to run on this router, and analyzes them based on the information in the image and what we know about Cisco. We have actually written this thing in .NET because I like .NET, and I didn't want to do the end case stunt of like getting owned with a corrupted file system. So this is why we're not using C. Now the thing is, the first thing that comes to mind is, well, if someone gets code execution and you write core, then he's just patching the core writing functionality and you're out. That is correct. So we also support memory acquisition over the GDB protocol, which is another developer feature unintentionally left in. So the boxes speak in the serial GDB protocol, which you can then use over the serial console to actually acquire the memory. It is very painful. Even more painful, but actually not patchable by any shellcode, is you break into the ROM1, into this kind of BIOS, and hex dump the entire machine, and then compile it back into binary. Be surprised, it works quite well if you got enough time. So what do? We take the iOS image that was supposed to run on the router. So you should not actually copy the image down and then compare it to the core dump, because that would be the same thing. So we're expecting that you have a uncompromised copy of your image, or that you can legally or less legally obtain one from the Cisco FTP server. We know this, and we need this image for two things. First, we need the header information to do the memory mapping and find out where in memory stuff actually is, because the core dump doesn't tell us. And we can also just go ahead and compare the things that really shouldn't change, like code. Code should actually not change in runtime. If it does, something really bad happened. So this is what we do. We take the header information and map it out on the core, and then we can directly compare code segment and read-only data, which allowed us to detect the first publicly disclosed rootkit. Topo from Core Security wrote a iOS rootkit, and he called it Dick. So we could actually see where it is, and he provided us with a patched iOS version, so we could actually test our code, because it's kind of boring to write a forensics tool and always try to detect your own chain codes. So it was interesting to see how we performed against others, and it worked quite well. So we can tell you that Topo's Dick is exactly 3 times 4. Now, essentially, those are the 3 places where he patches the iOS image. What he does is the classic thing of patching the functions that tell you if passwords matched or not, to always return 1. So once you have that information, you can actually take the core file, load it into IDA, and just don't disassemble anything except for go to this virtual address and press C, and the only thing that comes out of it is the rootkit. And everything that's still data is not the rootkit. So it's really easy and useful. If anyone wants to see the full report, in SIR Online, there's a case number that you can enter, and then you see the case. Yeah, I hang around way too much with Rudy, so I use long hashes. But that's my fault. So what we also do is we take this memory dump and reconstruct the entire heap, because the heap contains a lot of metadata. What's cool about this is, because they all share one heap, what they do is they go and write on every heap block a string that actually says what this heap block is used for. And pretty much like if you're living with other people, you label the stuff in a fridge. That's what they do, so they can blame each other. If someone overflowed his buffer, they can say it was your heap block that spilled into mine. This is really useful for the forensics approach, because we now know what each heap block is and what it is supposed to do. The problem is, once you start analyzing something like this, you base it on the assumption that, well, they have a common heap, it's a double linked list, they will not go anywhere else, and it will be integrity checked, and it will be fine. Wrong. People have very interesting ideas, like this. I have the firmware for the ISDN line card of my router in the read-only memory, in the read-only data section of my program. Now, since I applied the firmware after booting, I don't need this memory anymore. So what I'm going to do, I'm going to free it by linking the read-only data section block that I just used into the heap. Which is great if your idea of an integrity check was, hey, let's first check if this memory that the heap pointer points to is actually in the heap area, because if it's not, then it is very much looking like one of the heap overflows I wrote. Well, here goes the check. So we ended up having most of the functionality or full functionality of the process called check heaps, which is the onboard integrity checking process on iOS. And we can find holes and stuff, yeah, essentially integrity check this heap. We also get the process list out, which also lives in the heap. And we can now go ahead and create individual stack traces for the individual processes, what iOS itself cannot do. Like when the box is popped, you don't see which process actually got taken over, because it's all one memory area. You can write anywhere, and you can easily jump from one process to another without even noticing as an attacker. So we needed individual stack traces to actually find stack overflows. And we find things like TCL backdoors, people use tickle backdoors for quite a while, especially if they used to work for an ISP and now don't. Because people tend to like their level of access that they have, and they tend to want to keep it. So tickle scripts are the tools of trade for network administrators to have access to their routers. They're very short scripts that essentially bind to a port, take the string that's coming in, put it into the shell, get a response out, send it back. Right now we're just dumping out the text from the tickle scripts because I have no idea how much I need to drink before I will start writing a tickle decompiler for the compiled stuff. Then there's this interesting thing about the iOS packet memory. So iOS forwards packets in many different ways. The slowest is process switching, which really goes to the CPU, and then there is like fast switching and particle systems, and then you have special hardware and whatnot. And at least all the access layer stuff uses I/O memory, which is carved out from the main memory. So you get actually core dumps individual for the I/O memory, which is cool because it contains ring buffers. The ring buffers are by size, like T-shirts, like small, medium, large, extra large, tent. And this is and this is what they do for packets. So if your network handles big packets all the time, like regular full TCP packets for downloading porn, then they end up in a different ring buffer than the small ones, like pings. So that means newer traffic doesn't actually erase older traffic in a linear way, but in a environment-dependent way. And they really try hard to not copy packets around in memory because that's slow. You actually find a lot of stuff. So what we can do is we can take the information that we have from the heap reconstruction, go to the I/O memory, and dump out the packets, which is useful because then you get a PCAP file. This was just captured from this box sitting in our office, so you see Windows blah blah talking. And you can turn all the traffic that went through this router in the recent past into a PCAP file. That is very useful because potentially if the box crashed because of the iOS exploit not working, it was caused by a packet coming in. Very rare case for a router. And this means since you're still holding all the pointers, you can find the pointers on the stacks of the process pointing to the packet, which means fuzzing now became really easy because you're just throwing shit at it, and when it crashes, you go like, give me that one packet that crashed you. So that is useful. And it can also like disclose information on, let's say you have a box that's sitting on an individual interface of a router, because the individual interfaces also have ring buffers. So if this box is sitting alone there and it's not too shady, then there's a long traffic history. And if this box got popped and let's say RM'd and like it's just empty, you can still go to the router and unplug it from the network, not from the power, and get the packets out, and then potentially see what popped the machine or who talked to it lately. So coming to the challenges. The challenge with iOS on both sides is the combinatory explosion of platforms, aka metal, iOS version, major version, minor version, release, special release, feature set, and additional hardware stuff that you can put into. So essentially, in production networks today, you're looking at over 100,000 different iOS images. Now, when you keep in mind that this behaves like a single program, and you probably realize that if you ever compiled your program and looked at it in your debugger, and then you changed the line in your program and compiled it again and looked in your debugger, it actually looked a lot different because all the stuff got moved. Now this applies to the entire memory space here. So you can't actually say where stuff is in memory. Even the stacks that, for example, on Windows exploitation or Unix exploitation, before address space layout randomization. You knew exactly in which address range the stack is, and then you just put an obsolete on it and then execute your code. With iOS, you can't do that because the stacks are blocks in a heap. The heap is actually on top of the data segment and is defined by the end of the data segment. So you would need to know how big the data segment is, and you would need to know how big the code segment is. Otherwise, you don't know where your stacks is to be expected. And then it's in the heap, so it's entirely unpredictable. This is really a great headache because we actually have to jump through many, many loops to get the address information out when we get a core file into SIR. But it's also a big headache for iOS exploit writers, which is why getting stable exploits is so expensive and hard to do. Yeah, this is what I just said, because remotely, you also have this 1 in 100,000 chance to figure out what iOS image am I attacking. And all the exploits so far had fixed addresses that they jumped to. And also, any exception that you cause, anything that doesn't work in your exploit, reboots the router. Which is shitty because like, on the Unix side, for example, there was exploits that brute forced because the server respawned over inetd, and so you could brute force the address. Well, with the router, you can't do that because the people in the network management center may be lame, but if this box is blinking red for half a day, they will probably notice, and half a day gives you about, what, 20, 30 attempts. So that probably doesn't hold. Yeah, I already mentioned that all the exploits published so far are for one fixed image with one specific feature set. So essentially, the fact that the iOS coders actually recompile this entire crappy thing, and yeah, there's a reason why iOS actually shows the name of the guy who compiled it when it boots, because everyone has apparently their own makefile, because the thing looks different if A or B just compiled the same image, which is why they have so many image versions. So their messed up build process is actually their best protection right now. This is what it comes down to. Because it is very similar to the source port randomization patch that everyone applied because Dan couldn't keep his mouth shut. So performing research in this area is crucial because it has always been on the open research side, has always been an issue that you couldn't really discuss shellcodes. I mean, people give talks on iOS shellcodes, but then they're iOS image codes because they only work for one image and they don't have stable code execution. So what are you going to do with your shellcode? So this was always a big issue. So we actually spent about a bit of time there to understand how the forensic side will actually look if we have stable code execution. So this is the question, where to turn to. If I overwrite the link register, the saved link register on the stack, we're talking PowerPC here, and return, I need to specify an address. And I can't be vague. I can't tell it to just jump near my code or something. So when we look at the memory layout, there is not much we can turn to. The first idea I had was jumping into I/O memory. That makes most sense because you're trying to execute the stuff that you send in with your packet, right? Oh, yes, so good. So we fumbled around a while, and we actually got it to work that we had an IPv4 packet that was valid and executable PowerPC code. Until I found out that the I/O memory is not executable. Should have checked that first. But the packet is cool. So in my desperate search for a place to jump to, I found the ROMmon code. Remember this BIOS thing that boots the device? This code stays in memory, and it stays at a predictable address. And it's not used by iOS. And the version distribution is a lot smaller. So because it gets shipped with the device, hence the name ROM. People can't update it. That's good. That is useful. So a quick search revealed that this is ROM on versions for the 2600. You see there are 8 entirely, like there are not more than 8. And they're shipping time dependent, of course. So most of them have the oldest code because bulk sales rocks. Cisco salespeople, Cisco is a fully sales-driven company. They make money on a provision, so they try to sell a lot of routers at once, which I highly appreciate because they're all going to have the same ROM on version. So return-oriented programming is something that I think pretty much every hacker that had a need for it invented by himself, and then was surprised that everyone else invented it too. So Sebastian Kama talked about this and called it borrowed code technique. There's an excellent talk from Black Hat this year on return-oriented programming, highly appreciated, because that was actually one of the academia talks where they actually did something right. And it has been shown to work very well on Intel's, of course, and on Spark. Now the problem is, what you do is you lay out the stack in a way, and then jump into individual functions that are already existing in the code. So you're not injecting actual code, you're just changing the stack so it behaves differently. I have fancy graphics in a minute, don't look puzzled. The problem we have here is it has been shown to work really well with an entire glibc and not the diet one. So we end up having a lot of code, and we have architectures that they use, like Intel, that directly return over stack. Now, in this case here, we have about 36,000 instructions because the bootloader isn't that big, and we return over the linked register. Sucks a bit, but worked nevertheless. So here's how it works. Essentially, you look for code segments in the function tails that you're interested in. Let's say you have this is the code that fucked it up, so here's the buffer overflow, I kept it out, and then you have a return, an epilogue that actually fixes the stack, restores the higher registers, and then you need an epilogue that actually saved the linked register on the stack, and here returns it with the pulling it into R0 and then putting it into the linked register. So you can't actually exploit very short functions because they don't save the linked register on the stack first. So you have your buffer that you can overflow, and then you fill it with stuff up to this point where the saved registers are, and then more stuff, and then you return to the function that you discovered before. This is a function in ROM1, and this is what you need. It's an arbitrary memory write. It takes, for those of you that don't speak, I was about to say PowerPoint, PowerPC. It takes the register R30 and moves it to offset AB to the address where R31 is pointing to. So that's an arbitrary memory write. Now, because the registers are restored here with the data that you put on a stack, they're actually used when you jump here. So you can actually put the value and the pointer into your buffer overflow and then jump to this function. Oh, I had it even better animated, shit. So this is where it pulls the information. Then we jump to this function, and then we have the memory write, ta-da. And then, of course, you can chain this. So you can do it again. So you feed it more crap and put this into the linked register, put this into the registers that get restored, and then jump back. That is a well-researched technique, but actually works on PowerPC as well quite nicely. Now, we have a second issue. We have too much cache. A rare problem in those times, but here we do. Except we have two different caches. The thing is, the data cache and the instruction cache are entirely independent. They don't inform each other when stuff happens. because the PowerPC designers figured that most code is not going to modify itself all the time. So what happens is you have your typical capital A's. You get them in here. You have a mem copy, which is hopefully too long. Then it goes back to the data cache. And then because he doesn't know if the data is going to be changed in 5 minutes or so, he's keeping them in the cache first, which is the purpose of the cache. So it looks like you wrote it to memory, but you didn't. So if you jump to it, it goes boom. And not boom in a positive way. Because it's jumping to the stuff that was there before. So you can't just like write stuff and then jump to it, which sucks. But there is more code in Ramon that we can actually use. Right in the beginning of booting, it actually doesn't want this cache either because it's unpacking the image. So there's an entire function that goes ahead and essentially says, are interrupts disabled? Let's see, disable interrupts, flush all the caches, turn them off, and turn interrupts back on so we have internet. It's cool, so we can jump there and disable the caches. So this is how reliable code execution on Cisco works. You have a stack and an overflow on a stack, right? Now, I'll probably win a prize here for the animation, I hope. It looks like a mess when you design it. So first of all, you return to the function that disables the caches. And you also return to it in the return-oriented programming way. So you're not jumping into the entry point, but you're jumping after it saved the registers on the stack so that you keep stack control. Then you have the return-oriented memory write. So you're writing a move to counter register SP into another memory area I discovered, which is the global data elements that are placed right in front of the image, so they're not image dependent. They're always at the same place, and it's executable and writable in memory. So we are writing this instruction there. Then, of course, we are writing another instruction, which says branch to counter that we just loaded with the stack pointer. And then we jump to this code, which then jumps to the stack, which we didn't need to know where it is because it's taken from the register, right? And then we search the entire memory for a tag. Now, what do you do if, like, Germany has this new trend of losing data? And, well, essentially what we have right now is we lost our data because we need the remaining packet to have the big shell code, right? So we do what most hackers do. We go to check Fefe block, and then if we find Fefe block in I/O memory, this is where our data is. So we copy this data from the I/O memory, because it's not executable, onto our stack, but on a higher range that is not used. And then we execute our third stage code. I so wanted to show that picture. So, notes on the reliability here. This method is actually reliable for a known bootstrap version. So, I did successfully test it and implement it for the IP options vulnerability, which is a very nice vulnerability, and I hope to show you in a minute. So it's a single packet buffer overflow in iOS. And I also successfully ported it to the FTP vulnerability that Andy Davis exploited, so that my version of his exploit actually is image independent. The second stage code, the one that looks for the block, is actually the less reliable, because here again we have this complexity issue with iOS that they actually place the code, place the memory anywhere they want. So I/O memory is sometimes at a different base address, even for the same ROM. But that's actually, you can overcome this quite easily by adding more second stage code, but you usually want to keep it small because you want to get away with it. After you got code execution, you actually want to keep the box running, because if you have code execution, then the box reboots, you've won nothing. So the people that have published exploits so far use terminate process, which is an image-dependent call, of course, because you don't know where the function lies. So this is exactly what we don't want. And, well, the vulnerability I was exploiting is IP options, which happens in a process called IP input. Now, this process is kind of crucial, because otherwise you have a pure IP output device, and that sucks. So actually terminating this process wasn't an option. But coming back to how our exploit looks like, we have the stack layout. And here's the reason why we try to be really small with the second stage code, because we can search the stack frame upwards and see if we find a sequence of saved stack pointer and link register that we didn't fuck up already. And then we return to that one. And this is reliable because the depth of the stack and the layout of the stack, especially in terms of what functions return information to functions is on a stack, is a call dependency. Like this exact call path will always produce the same stack trace in terms of what functions are on there. So they will actually need to change the code logic of that exact code path. So this would become unreliable. And it also includes some voodoo that tries to make it more reliable. Shall I demo this? Yeah? This is the point where everything goes wrong, right? We want to see the packets. So it defaults to the most useful packet. What do we have here? Okay, that's good. Now, how was I thinking this works? Oh yeah, one word to the demo. Blah, 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 Shut up. Yeah, it's talking too much. Better. So the thing is this, when we had all the discussions with the government people on the hacker paragraphs, we had pretty much no agreement with them except for one thing, that Hello World programs are not hacker tools. So, since I cannot actually demo this with a shellcode, which is illegal, we have a remote string display program for Cisco iOS. So this is the box. This is the Cisco. Yeah, I'm using the mouse for pointing. And this is my Linux in a virtual machine. And we're just like firing the exploit display program. And we get a statement down there. So what's really cool about this is it's one ping. And it's actually even a valid ping. So the vulnerability lies in the fact that they fucked up to parse the IP options correctly. So what we have here is down there. We have the option EOL, which is end of options, which is a 0. But then following this, there's a source routing option, and the length of the source routing option is actually used because they try to be clever when they answer the ping. They look at the ping and go like, oh, it's source routed. And it's a network test tool. So we should actually answer the same way back. So they're trying to turn around the source route. And the RFC says that the source route can only have 8 hops in it. So they have a buffer, and, well, they were generous. It fits 10. But the length field obviously allows for more. So this is the buffer overflow, and then like the remaining stuff goes onto the stack, and the data here is then all the voodoo I just told you. Essentially, it doesn't just work on PowerPoint. Let's keep going. So, yeah, another disclaimer 202C. Because for an entirely unrelated reason, we're now looking at the problem of, well, we have image-independent code execution, so we better have not image-dependent shellcode, right? So the earlier exploits use fixed offsets for data structures and stuff. It looks nice, but yeah, with a fixed offset, it's always easy. Andy Davis published a signature-based shellcode that goes through the code and through the iOS code and looks for a certain byte sequence and then guesses this is the call he's trying to patch. But he's still using fixed offsets in the data structures he's then patching, which is relatively unclever. When we look at shellcode for iOS, we usually want to patch some functionality out of the image. And that means we just load the image into IDA, wait for half a day, and then search for a string that references something that we need. For example, it says bad passwords. And then we cross-reference that string to the code that references the string, and then we know what function will actually verify the password. Well, we can do that shellcode, right? We find a unique string. We partially disassemble the entire image and look for references to that string. And then we go backwards from that point to the setup instruction for the function right in the beginning and override it and say return true. This is how it looks like. This is actually quite useful because you can feed it different strings. You can say like ACL match drop, or you can say bad passwords, or whatever the functionality is that you want to always return true. You specify it by a string. So what other options are we having right now? So this is essentially what I'm starting to look at now. Is now we get stable code execution. What should shellcode actually do? What is expected of evil people to do with their shellcode? The classic thing is VTY port mines, like really interactive shells, or connect back shells. The problem is those patches have very little possibilities to actually figure out how the box is configured, and there are gazillion ways to have weird Cisco configurations. So the shellcodes published so far also have no consideration for AAA configs. So if the admin of the Cisco has more than one, they probably have a central radius or TACX server, and that's called a AAA configuration, and those shellcodes actually don't give you access after that. I have one that uses the one packet, one command way, injecting a command string for the iOS shell into the function that executes it, and then just do nothing. So that can be used. It's more flexible. You can configure the box individually, step by step from the outside. Problem is you don't see anything. But you don't want a backchannel in many cases. And image patching shellcode is still the most powerful and reliable method. And it's also the one that our forensics tool attacked. So, summary. The best defense is still to block all the traffic to your routers. Like, if someone is talking not through, but to your router, it's potentially me. iOS forensics tools, at least the one we wrote, are right now capable of detecting most of the mischief that we can come up with. If it persists, if you have a one-shot exploit that, for example, just executes a single command, it's not persisting, there's very little chance you're going to detect that, no matter how much IPS, IDS, whatever, logging and whatnot you put in your network, it's very unlikely that you will see my one ping packet. Reliable code execution is finally proven, at least on PowerPC, because I just got the MIPS boxes. And it's highly likely that $bad guys have a lot better exploits than I am, because it would be fairly arrogant to assume that I'm the best in this area. So here comes the things. First, Nicolas Fischbach actually had pointed out the bootloader and Ramon code at pH neutral. I guess he's hating himself for that because he's responsible for the security of a large Cisco-driven network. Mac and sold for finally Cisco equipment. Then there was an initial question from a nice fellow in China who sent me the packet capture that actually triggers the IP option vulnerability and asked me why he couldn't return to the stack. And yeah, Dynamics for their voodoo tools, no win for defending all the time. To put in Mumpy for general awesomeness. And finally, Ilker from PCERT, because I happened to attend a Cisco meeting where PCERT gave a presentation on iOS security and exploits without the word Finlit in it, which is very motivating. I think that was it. Yep.